All right, so far we spoke a lot about data. We spoke about big data, strongly consistent data, just now data produced by ML model. Let's switch the topic a bit and let's talk about compute. In the next talk, Kenny will discuss how we do large-scale cluster management at Facebook using Tupperware. Please welcome Kenny Yu.
Hi, I'm Kenny, and I'm a software engineer at Facebook. In this session, I'm going to talk about how we're scaling cluster management at Facebook with Tupperware. Today, we've heard from some amazing speakers about some of the scaling challenges they've faced over the years. And I'm very excited to share with you our journey over the past 8 years as we scaled Tupperware to support Facebook's growth. In this session, I'm going to talk about how we view cluster management and how Tupperware fits in that picture. And then I'll talk about how Tupperware has evolved over the past 8 years and some of the lessons we learned along the way. And then I'll end with some upcoming challenges. So what is cluster management? At a high level, it's how we manage our computing infrastructure in our data centers. Over the years, we learned it's very important to understand who your stakeholders are in the system because it's their needs that drive the evolution of the system. At Facebook, we have 3 major stakeholders. So show of hands, how many of you are developers? You own a service at your respective companies? So what you probably care about in a cluster management system is developer productivity. The system should make it easy for you to manage and deploy your applications at scale. Show of hands, how many of you are capacity engineers? Some companies might call them efficiency engineers. What you probably care about is increasing the efficiency of your resources. And lastly, how many of you are data center operators? Oh, I see, yeah. So what you are responsible for the physical hardware in your data centers. And as a result, you want the cluster management system to make it easy for you to perform hardware maintenance. So how does Tupperware fit into this picture? What is Tupperware exactly? Well, we use it to store food, but it's also Facebook's cluster management system, and it's been running in production since 2011. Tupperware is many things depending on which stakeholder you ask. For developers, it's a container deployment platform. It's how we start and stop containers and how we orchestrate them at scale. For capacity engineers, it's a resource scheduling and management platform. It's how we do admission control and ensure that resources are being utilized effectively. For data center operators, it's a machine maintenance platform. Data center operators depend on Tupperware to spread their containers appropriately and to move containers around when they need to perform maintenance. At this conference last year, we spoke in depth about how we set up containers on individual machines. This talk will focus on the layer above that, how we manage containers across many machines. Tupperware has evolved a lot in the past 8 years based on the needs of these stakeholders. So for the rest of the talk, I'm going to walk you through some of the largest milestones we've had in our history and some of the lessons we learned. So let's rewind the clock 8 years. In 2011, one of the largest challenges we had was operating a service reliably at scale. And there were many reasons why operating a service reliably was difficult. First, there's no standard way to perform failover. Every team either reinvented how they did failover or they just lived without it. Another challenge was that reproducing the production environment was difficult. Applications would run on bare metal, and there could be other services running on that machine that might interfere with their workloads. Tupperware was created to address these challenges. Instead of running applications on the bare metal, we run applications inside containers for better isolation and reproducibility. We also introduced a control plane to make it easier to handle deployments and failovers and more. To understand how we deployed our Tupperware, we need to first take a look at how our data centers work. So Prineville, or PRN, is one of our data center regions, and we have many of these across the world. Within a data center region, there could be multiple data center buildings, designated PRN1 and PRN2 in this diagram. And within a single building, we might have multiple clusters. At this time, a cluster had a physical meaning. It was a group of racks connected under a common network switch. The Tupperware agent is running on every machine at Facebook, and it's responsible for starting and stopping containers. Above this is the Tupperware scheduler. This is our control plane that's responsible for starting and stopping containers, performing deployments and failovers. Embedded inside the Tupperware scheduler is the Tupperware allocator. This is the component responsible for mapping containers to machines. And note the slight terminology difference from our terminology and what is commonly used externally. The Tupperware scheduler corresponds to a control plane in external terms, and the Tupperware allocator corresponds to a scheduler in external terms. And this worked very well. The Tupperware allowed developers to easily manage their applications, and Facebook has grown a lot since then. As Facebook continued to grow, we hit another challenge. As we built more and more data centers, we had more clusters. And over time, hardware in our clusters need to be refreshed. In order to upgrade to hardware with new generation of hardware, we need to decommission clusters. And decommissioning clusters was challenging for everyone involved. First, there was no way to automatically move workload from one cluster to a different cluster. And so there was a lot of manual and tedious and time-consuming work for developers to stop their workload and restart it in a different cluster. Because of how tedious and time-consuming this was, many resources in our data centers were just sitting idle during the decommission process. And because of how tedious and how much manual work was involved, it was very unpredictable when the decommission would finish. To address these challenges, we introduced regional schedulers. Whereas before, a machine had a fixed binding with the scheduler for its cluster, regional schedulers break this fixed binding. Here, the idea is that the mapping between a machine and scheduler can be dynamic. Any scheduler can use this machine, but only one scheduler at any given moment. And here's how we use this idea. So here we have cluster schedulers as we did before, and we introduced a new regional scheduler in the middle. When that regional scheduler wants to use machines to start or stop tasks, to start and stop containers, it will borrow machines from the corresponding cluster schedulers. As part of the borrowing process, the cluster scheduler will stop managing some machines and give them to the higher level scheduler. Now that regional scheduler can start and stop tasks as they normally would. If a user starts a Tupperware job on that regional scheduler, it can now span clusters, data center buildings, and even regions, resulting in global schedulers. And as a result, we allowed Tupperware users to declare their intent on how they should spread their containers across these fault domains. It's also worth noting that in the early years of Tupperware, a large focus of the team was on adoption and proving its value. As Tupperware matured and became mission critical at Facebook, we began focusing more on reliability, stability, and operational excellence. This allowed us to increase the pace of changes in the coming years and work on bigger problems. And one example of a bigger problem is in 2017. In 2017, machine maintenance became a much more pressing issue. As our infrastructure continues to grow, there are almost always machines going in and out of maintenance. This could be for kernel upgrades, network switch upgrades, server repairs, and cluster decommissions itself is also an example of maintenance. And this was difficult for multiple reasons. First, workloads might configure different policies on how they should behave in the event of maintenance. Some applications might choose to stay, some applications may choose to move, and sometimes it can be difficult to reason about what should happen. There's also many fragmented workflows at this time at Facebook to perform maintenance. It has made it very difficult for developers to understand why their workloads might have been affected by maintenance. And it made it difficult for data center operators to understand why maintenances were not proceeding. To solve this challenge, we introduced a new standalone service called Resource Broker. And the goal of Resource Broker is to be the source of truth about all machine information and maintenance events, and to coordinate all maintenance workflows at Facebook. So to understand how we use Resource Broker, let's take a look at this diagram. Before, we had regional schedulers borrow machines from the lower level cluster schedulers. Now with Resource Broker, both types of schedulers get their machines from Resource Broker. And once they've obtained their machines, they can start and stop containers as they normally would. And if a maintenance event needs to occur on a machine, Resource Broker will notify the corresponding scheduler to move or take the appropriate maintenance actions. With the introduction of Resource Broker as a source of truth about machine information, and with our users shifting from using cluster schedulers to regional schedulers, there is no longer any need to keep around cluster schedulers anymore. And our team is super excited to finally get rid of cluster schedulers in our fleet. We're super excited because it simplifies our system, and this means we've completely evolved from the architecture we started with in 2011. And this was made possible by the years of hard work focusing on reliability, stability, operational excellence that enables these bigger changes. So as Facebook continues to grow, the amount of workload within a single region continues to grow as well. And we started hitting some scalability issues, just having a single control plane managing all that work. Historically, machines at Facebook were divided into fragmented, dedicated server pools for different teams to use. And so we leveraged this idea, and we leveraged this to our advantage. We ran multiple independent schedulers in a single region, where each scheduler handled a different subset of machines. This allowed us to continue to increase the amount of work that we can handle within a single region, but it also added some complexity. This was not transparent to our users, and this added complexity into job management workflows and capacity management workflows. As we continue to increase the size of our fleet, underutilization of resources becomes a bigger and bigger issue. At Facebook, there's 3 major sources of underutilization. To understand these 3 sources, let's first take a look at a graph. On the x-axis, you have the time of day, and this blue curve represents the capacity utilization throughout the day. Many large services at Facebook have this pattern, where the utilization correlates with the amount of users currently actively using Facebook in the world. Services are typically provisioned for peak, and during off-peak, there are some resources sitting idle. In addition, when we provision resources for a service, we usually include some buffers for disaster recovery events, so unanticipated events in our data centers. And then lastly, we might have some resources in our data centers that we have not yet allocated to any team. So all 3 of these sources of capacity we could reuse potentially to do more important work. Many Facebook products can use these spare resources to improve the experience for the end Facebook user. So how many of you have seen these year-end review videos? Yeah, so these videos, the system that generates these videos, used spare resources obtained through our Elastic Compute system. And before I talk about our Elastic Compute system, let's first take a look at some of the challenges in utilizing spare resources. So on one hand, you want to make it easy for developers to utilize these spare resources. But on the other hand, you want to make it easy for you to take back these resources to run more critical work. And there are many approaches in the industry to improve utilization. So let's take a look at the solution space. In the solution space, here I have 2 axes. On the x-axis, I have what I call leverage. And by leverage, I mean how much influence you have over developers to optimize their service. And on the y-axis, I have size of machines. When you have high leverage over your developers and you have small machines, it makes sense for them to optimize their whole machine. You get the whole machine, you optimize everything out of it. When you have low leverage over your users, you need to solve the utilization problem at the infrastructure level. And this is typically done through stacking containers together. If you have large machines, you can use a combination of both stacking and resource overcommit. And when you have high leverage and large machines, you have many more options. You can do all of the above and maybe more. Facebook falls in the upper half of this diagram. At Facebook, one of the limiting resources in our data centers is power. As a result, we prefer to use smaller, more power-efficient machines that give us more resources in aggregate. And for our large services at Facebook, our capacity engineering organization has a large amount of influence to influence these teams to optimize their services. And they've optimized for a whole machine use case. For the long tail of smaller services at Facebook, we don't have as much leverage just because there's too many small services. And the way we improve utilization there is by stacking. Large services are both the largest donors of spare capacity and are also the ones that could benefit the most by utilizing spare capacity from other services. And since large services at Facebook are already optimized for the whole machine use case, we use a whole machine as a unit of capacity shift. And to utilize these spare resources, we created what we call recallable schedulers. And the idea here is that resources can be recalled at any moment. And a resource here is the whole machine. So here's a diagram to illustrate this idea. On the left, you have a normal critical scheduler running a critical service. And on the right, you have a recallable scheduler running jobs that are utilizing spare resources. And now suppose a service under the left scheduler experiences a load spike and now needs to use more resources to satisfy the load. It will coordinate with resource broker to get more machines. And if it needs to use that middle machine, resource broker will recall the machine back from the recallable scheduler. As part of the recall process, the recallable scheduler will kill any workload it has on that machine. And now the more critical scheduler can use that machine as it normally would. And all of this can take place in under a second. This elastic compute approach works really well when you have a large shared pool of resources, and any machine can be used to run any other service. But because of a historical fragmentation, this was not of machines into dedicated server pools, this was not always easy. And one large reason for this historical fragmentation is to support stateful services. In 2018, one of the last remaining blockers for supporting WhatsApp in Facebook infrastructure was to support the backend services that support WhatsApp. And many of these backend services are stateful. And this introduces new challenges. And to understand what these challenges are, here's an example. Let's say we have a stateful service, and many stateful services typically are composed of multiple data shards. In this example, we have 4 data shards, A, B, C, and D, and each data shard is replicated twice. And we're running 4 containers to host all of these shards. And now suppose a maintenance event needs to occur on machines that are running container 0 and container 3. If we allow this maintenance to proceed, this would render both replicas of data shard B unavailable. And now the service might experience some downtime for its users. This example shows the problem or the challenges with stateful services. In a stateful service, the containers are not homogeneous. And it matters which exact containers you take down. You can't just take down any n containers. And this makes deployments more difficult, and it makes data center operators' lives more difficult because it makes it harder to perform maintenance. Tupperware needs higher level knowledge about the application's data placement to make more informed and safe decisions about which containers it should update. And to do that, instead of building this logic into the Tupperware scheduler and making it more complicated, instead we provide an API, a pluggable API called task control. And the idea here is that we can delegate control externally. If a stateful application wants to integrate with Tupperware, they can provide a controller, and whenever Tupperware needs to perform container lifecycle operations about updates or moves, restarts, or drain events, the scheduler will notify this external controller. As an example, WhatsApp has an external controller that controls many of their Tupperware jobs. And when container lifecycle operations need to occur on their jobs, the scheduler will call out to their external controller, and their external controller can say it's OK to proceed, it's safe. They can reorder operations as needed, so maybe there's a different order in which things need to happen. Or they can temporarily delay operations while they drain state. so move some of the shards to a different replica. In addition to WhatsApp, one of the largest users at Facebook that uses task control is Shard Manager. Shard Manager is a programming framework at Facebook to build stateful applications, and many critical stateful applications are built on top of Shard Manager. And some examples include key value stores that act as persistent storage for many critical services at Facebook, monitoring stores that store all our production counters, and the backend services that support Messenger and Marketplace. While Tupperware allows developers to specify how their containers should spread across data centers, Shard Manager provides a level of abstraction higher. It allows developers to specify how their data shards should spread across their containers. Tupperware and Shard Manager work together through task control to make it easy for developers at Facebook to manage and build stateful applications. And note that task control is not limited to supporting stateful services. As an example, the web tier, the website that's pushed continuously every day, is stateless, but it uses task control to dynamically update their push pace depending on load throughout the day. So with some of the biggest blockers to consolidating our fragmented pools, last year at this conference, we announced our mission to support a global shared pool of resources. And supporting a global shared pool of resources introduces new challenges. With more and more data centers being built per region, and with our shift to using smaller machines, this means that there are many more machines per region. And one scheduler is no longer scalable enough to handle all of those machines. Even if it could, there's a large risk just having one control plane. As Ben mentioned earlier today, we can either scale up or we can scale out for better reliability. And then lastly, we did run multiple independent control planes, and we learned that it's very important to maintain one entry point for a region, because this simplifies developers' workflows and capacity management workflows. To solve these challenges, we internally shard the scheduler. And the idea here is that we run multiple control planes as one logical control plane. And to do this, we made a couple of changes. First, we externalized the Tupperware allocator as a standalone service. This allows us to maintain one unified view over all the resources in a region, and also allows us to independently scale the Tupperware allocator and the Tupperware scheduler. Next, we run multiple shards of the Tupperware scheduler, where each shard manages a different subset of jobs in the region. As the number of machines grow, as the number of jobs grow, and the amount of orchestration workload grows, we can add more shards as needed. And to maintain a unified view of the region for our users, we put a proxy in front to fan out and aggregate the information. From the user's point of view, the proxy and the schedule shards are one logical control plane. And then lastly, we have a Tupperware front-end service to provide higher availability and to orchestrate some common workflows. So Tupperware has evolved a lot over the past 8 years, and we learned many valuable lessons along the way. We hope that some of these lessons might help, and we hope that some of these lessons, you might be able to use them in your own organizations as you scale your own infrastructure. So with regional schedulers, we learned that it's a very powerful idea to allow a flexible binding between machines and control plane. This is how we scale beyond a single cluster. This is how we simplify fault tolerance reasoning for our developers, because they can specify how their containers are spread across fault domains. And this is also our mechanism for making use of elastic compute. With task control, we learned that it's a very powerful idea to delegate control externally. You can maintain a relatively simple control plane while still supporting stateful applications and their complicated requirements. And with sharded schedulers, we learned that it's possible to manage a very large fleet as a unified entity without adding additional complexity for our users. Finally, here are some upcoming challenges that our team is excited to tackle next. As more applications move into our shared pool of resources, Many of those applications require storage. Their containers require some storage systems. There's a whole huge spectrum of different solutions we can provide, and it's unclear which one is still the best one, or maybe we should provide many different types of solutions depending on users' needs. So what are the right abstractions we should expose for storage in this highly dynamic environment, if containers are frequently moving around? It's very important to continue to increase the efficiency of our fleet. And we have elastic compute, but there's a long ways to go to continue to increase our resource efficiency. What are the right policies for demand control, and how do we continue to increase utilization? And for data center operators, how can we make our services resilient to large fault domains? In the past, clusters was our biggest fault domains that we could reason about. Now that we've moved beyond clusters, our next largest fault domains is a unit of power. What abstractions should we provide for our developers to make it easy to reason about fault tolerance of their service and make them highly reliable if, let's say, one of these power units becomes unavailable? So if any of you have answers to these questions or have any other questions, I'll take them now.